Okay, let's take a look at question 29 in topic set 5. In this question, we were given a reaction 4NH3, 5O2 going to 4NO and 6H2O. The way the reactants are placed is into the container that looks like this, that was originally separated with this stopcock, and then when they're open, the two gases mix, and then the reaction happens. So there's two steps here that you need to think about, because the reaction doesn't immediately happen. So when they're separated, there's no reaction. When you first open the stopcock, there's really no reaction, but what happens is that the oxygen, which was originally at 1.5 atmosphere, in 1 liter, now all of a sudden has a total volume that's much bigger, which is 3 liters, right? So the gas that originally has a pressure of 1.5 atmosphere is now going to have a reduction in the pressure because the volume is bigger. That's just Boyle's law. And the same thing happens with the ammonia, initially at 0.5 atmosphere at 2 liter, but now it becomes 3 liter, so the pressure also going to drop. So step 1 is to calculate the new partial pressure of each of these reactant gas after you open the stopcock. That's just Boyle's law. P1 V1 equals P2 V2. The temperature is constant, and then of course the number of moles doesn't change because you're still in the same container, so the number of moles is the same, the temperature is the same, so you can use Boyle's law. So let's calculate the new pressure using this equation. So if we do this for ammonia, our old pressure is 0.5 atmosphere, volume was 2, and the new volume is 3 liter, right? And that gives us 0.333 atmosphere. If we do oxygen, different numbers here, so 1.5 atmosphere, 1 liter, and then total is still 3 liter after you open. This one gives us 0.5 atmosphere of oxygen. Okay, so that's the actual starting quantity of each of the gas. The second part of this is the reaction itself. Now the reaction occurs in this whole container right here, which means that volume stays constant during the reaction. What else stays constant? Well, temperature. So constant volume and temperature. I'm going to start with our ideal gas equation with condition 1 and 2 being before reaction and after reaction, but since volume and temperature are constant, we can cancel out volume and temperature, leaving us with this equation, which you've seen before in other videos on gases. Not only can you write it that way, but more importantly, you can write it this way. What this is telling you is that you have mole ratio on this side, but that's the same as pressure ratio. And where'd you get mole ratio from? Well, you get mole ratio from your stoichiometric coefficients, which you have in your reactions right here, right? So these numbers that I have here as equations can also be thought of as ratio of pressures as opposed to ratio of number of moles. What the question is asking is how much NO is produced, which is one of the products, after the reaction is complete. Well, I know that I'm starting with each of these reactants at 0.33 and 0.5 atmosphere. So what I need to figure out first is which of these two guys is my limiting reactant. Let's determine limiting reactant. We can do this by taking each of those gas reactant and dividing it by its coefficient, because the coefficient now represents pressure as well. First, we're going to start with NH3. So we start with 0.333 atm NH3, and we go back to our equation. The equation says we're going to use 4 atm of NH3 per reaction, okay? And that gives us 0.08325 reaction. And then let's take a look at oxygen. The oxygen was 0.5 atmosphere, and the coefficient for oxygen in our equation is 5 atmosphere oxygen per reaction, and that gives us 0.1 reaction. So NH3 is our limiting reactant. We can then use that to figure out how much product we're going to make. I'm going to say pressure of NO produced is going to be, this is the actual amount of NH3 you have, 0.333 atmosphere of NH3, and then multiply that by the stoichiometric ratio, but now expressing that in units of atm. So NH3 and NO, and then looking up the actual coefficient, it is 4, which is 1, right? But that cancels this out, so you're left with, this goes away, 0.333 atmosphere of NO.